Hello, my name is Yuliang Huang. Today I will present our work on Similarity-aware Probabilistic Embeddings modeling, a new framework designed to improve video-text retrieval by explicitly modeling semantic uncertainty. Video-text retrieval typically relies on deterministic embeddings mapping videos and text into fixed points in a shared space. However, we observe a critical limitation, semantic overclustering, where visually dominant yet uninformative patterns cause semantically distinct videos to collapse into nearby regions. This severely reduces discriminability, especially under short or ambiguous queries. To address this issue, we propose SPEM, a similarity-aware probabilistic framework that represents embeddings as adaptive semantic distributions rather than static vectors. Our approach consists of three key components: cross-modal attentive fusion, adaptive semantic distribution alignment, semantic distribution range optimization. Together they form a unified probabilistic retrieval framework. We begin with cross-modal attentive fusion. Instead of mean pooling video frames, we adopt a query-guided transformer aggregator that allows each text query to attend selectively to the most relevant visual content. This design suppresses dominant but irrelevant patterns while preserving fine-grained cues. Importantly, this fusion stage establishes a semantically stable foundation for subsequent probabilistic modeling. Next, we move beyond deterministic representations. We project both video and text embeddings into Gaussian distributions, where the original embedding serve as fixed means and only the variances are learned. This anchoring strategy prevents semantic drift while enabling flexible uncertainty modeling. However, the key question becomes, how much uncertainty should each embedding have? To answer this, we introduce similarity-guided variance adaptation. By leveraging both frame-level and video-level similarity signals, the model dynamically expands or contracts each modality's semantic range. Intuitively, videos benefit from larger variance to capture semantic diversity, and text embeddings require tighter distributions to preserve precision. This modality-aware uncertainty control effectively mitigates semantic clustering. Traditional contrastive learning operates on fixed embeddings and cannot fully exploit distributional representations. We therefore propose a semantic distribution contrastive loss that replaces static vectors with samples drawn from the learned distributions. Additionally, we introduce boundary embeddings, which explicitly define the semantic margins of each distribution. These boundary-aware objectives regulate both the scale and direction of semantic dispersion, resulting in embeddings that are simultaneously more expressive and more discriminative. Extensive experiments demonstrate that SPEM consistently outperforms strong clip-based baselines across multiple benchmarks. For example, on MSRVTT, we achieve a 4.4% improvement in recall at 1 over the previous best method. More importantly, these gains come with nearly identical computational cost, indicating a favorable accuracy-efficiency trade-off. We further analyze where the performance gains originate. Replacing deterministic embeddings with probabilistic ones consistently improves retrieval, and modeling both modalities as distributions yields the largest gain, confirming that uncertainty modeling is the key driver rather than architectural changes. We also evaluate the boundary weight that controls the semantic range of each distribution. Performance peaks at 1, indicating an effective balance between flexibility and constraint. Overall, these results show that controlled probabilistic modeling is the main reason for our improvements. We study the effect of temporal evidence. Performance improves substantially when increasing sampled frames from 6 to 12 and suggests an optimal balance around 18 frames, beyond which returns diminish. This indicates that richer temporal context is beneficial only when the representation can effectively utilize it. Further analysis reveals two important insights. First, moderate video uncertainty correlates positively with retrieval accuracy, confirming that adaptive dispersion enhances semantic flexibility. In contrast, excessive text variance harms performance, validating our modality-specific design. Second, probabilistic embeddings significantly enlarge the similarity gap between positive and negative pairs, leading to better alignment structure. In summary, SPEM introduces a similarity-aware probabilistic paradigm that mitigates semantic clustering and enhances cross-modal discriminability. We believe this work highlights the importance of uncertainty-aware representation learning for future multimodal retrieval systems.